Dry gas reservoirs are fairly simple in the sense that their initial gas in place may be calculated using a gas-material balance, as long as water influx and rock compressibility are accounted for when necessary.
The material balance equation for a gas reservoir with no water influx can be expressed as G sub P times B sub G equals G times the quantity B sub G minus B sub G I. That is, the gas produced expressed in reservoir volumes is equivalent to the expansion of the gas in place. B sub G, the gas formation volume factor, is the volume which 1 standard cubic foot of gas occupies in the reservoir and may be expressed in terms of the gas equation of state. Thus, B sub G equals C times T sub R times Z divided by P, where C is a constant depending on the chosen standard conditions and the unit system. For example, for standard conditions of 14.7 psia and 60 degrees Fahrenheit in the English unit system, C equals 0.005. For the same conditions in the SI system, C equals 0.35. Substituting this definition into the material balance indicates that the gas produced, G sub P, is equal to G, the original gas in place, times 1 minus the ratio of pressure and Z factor at current conditions, divided by the ratio of pressure and the Z factor at initial conditions.
This equation shows that a plot of P over Z versus G sub P on rectangular coordinate paper should result in a straight line. The extrapolation of the straight line to any P over Z value gives the total recovery at that pressure value, and the extrapolation to P over Z equal to 0 gives the initial gas in place. If water influx is present, the material balance equation must include a water influx term. Since W sub E is a function of pressure and time, our plot of P over Z versus G sub P will not give a straight line, and an extrapolation of the pressure production data may yield an erroneously high estimate for G.
In the case of abnormally pressured gas reservoirs, the rock compressibility acts to maintain the pressure at a relatively high value by reducing the pore volume as gas is produced. The plot of P over Z versus cumulative gas production for these reservoirs will thus show two distinct slopes. The early slope exists during the period of abnormally high pressure, and the later one characterizes the reservoir when the pressure reaches the normal value. If only the first slope is defined, the engineer is advised against using the P over Z technique, since it will result in an erroneously high value. However, the material balance equation may be used if the compressibility terms are added. If the second straight line is adequately defined, it may be extrapolated to obtain an estimate of the initial gas in place.